Our second speaker is Daniel Ries. He is a senior member of the technical staff at Sandia National Laboratories, where he has been since 2018. His roles at Sandia include statistical test engineer, technical researcher, project manager, and a short stint as acting manager of the Statistical Sciences Department. His work includes developing explainable AI to solve national security problems, applying Bayesian methods to include uncertainty quantification in solutions, and provide test and analysis support to weapon modernization programs. Daniel also serves as an adjunct professor at the University of Illinois Urbana-Champaign as an instructor and mentor for statistics majors interested in pursuing a data science career in the national security enterprise. He received his PhD in statistics from Iowa State in 2017. Please join me in welcoming Daniel Ries.
All right. Thank you, everyone, for being here today. So today I'm going to be talking about adaptive design, specifically Bayesian adaptive design, kind of with an application to a specific problem that we worked on at Sandia, and then with some other implications as well. Okay, so we're at DataWorks. Of course, I'm sure you've already heard several presentations on design of experiments, and it's probably a part of many of your daily lives in terms of your daily work. And so oftentimes we're in situations where we need to gather a lot of information either quickly, cheaply, efficiently, and we're always going to be resource constrained, right? If you're a statistician, you're probably always going to be trying to get more data, and people on the other end are trying to get you to do more with less data, right? And so what I'm going to talk about today is an application that's kind of with design of experiments in physical testing. So we actually have like a thing that we can hit with a hammer, for instance, that type of testing. Although the concepts, to computer experiment, design of experiments, it's effectively all the same. And sometimes I think you can get lost in that between these two things, but effectively you're really working on the same type of problem. Okay, so a lot of traditional design of experiments is going to be static. It's the traditional way of designing an experiment before gathering data, analyzing it. But there are many situations where this static nature could be unnecessary, right? You might want to be a little bit more flexible in the way you design and carry out your experiment, and for reasons of efficiency. You might be able to do your test sequentially. Okay, and so that's what I'm going to be talking about today. All right, so to give you just a motivating problem that I worked out at Sandia. So one thing that we test is kind of the compatibility of certain weapon systems on aircrafts. So these warheads or bombs need to be able to be carried and then released from the aircraft safely, right? For both the weapon itself and, of course, for the airplane and the pilots. Okay, so there's a lot of different metrics that we're going to calculate to make sure that there's a safe separation here. And you could imagine that doing this on a live aircraft would be incredibly expensive. And so we like to do certain things in the lab. And so here's an example. There's a couple of pictures here of, there's a kind of a mock-up of a bomb kind of connected. And you can kind of see there's this almost like thing connected to it. And what this is going to simulate is essentially the release of a bomb, right? It's going to pull this kind of metal thing down a track really fast, and it's going to disconnect some cables, right? And as part of that, it's going to measure something that I'm just going to generically call a timing. And what we're interested in is making sure that that timing is going to be within a requirement. So this timing has to be between some amount of time A and B, right? And that's going to have some reliability requirement that says, well, you need to be able to say with some degree of probability that the timing of that release will be between A and B, okay? And so even though this is a lab test, this is also relatively expensive to run. And so we don't want to have to do these polls over and over again. So just to give some context, a test like this with this kind of lab setup, typically there's going to be, 7 or 8 test engineers working on it. Okay, and you can maybe run one test every or one pull every 10, 15, or 20 minutes. Okay. All right. So they kind of came to us and asked, how many samples do we need to test this reliability requirement? So the standard kind of approach that we could do is, right, we could kind of determine the sample size that we need using some sort of power analysis, right? We could design that experiment using a t-optimal design or whatever you want, right? Then give that to the test engineers. They go collect the data, right? Run the entire series, come back to you, and we can do the analysis. Okay. So that's a pretty standard way that we could do this experiment. And in this situation, that is the original way that we did the experiment. But that doesn't need to be the only way, right? We can also be adaptive in our approach, okay? So we could still start out with an originally designed experiment where, again, we do the same power analysis. We come up with some design that could be de-optimal. And what we could do is we could collect some amount of the data, say 10% or 20% of the data, right? And then we can look at the data from, taking a Bayesian perspective and kind of do some sort of analysis that might be able to allow us to, even after just seeing 20% of the data, stop the experiment, right? And make some decision of effectively like rejecting a null hypothesis or failing to reject. You also might conclude that we don't know, right? And then we can go around the loop, collect some more data, right? Do kind of the same analysis, check again. Do we have enough information now to stop the test, right? If the answer is yes, you can stop, make your conclusion. If no, again, keep kind of going around and around, right? And what this allows us to do is potentially stop the experiment early and save, obviously, time and labor, but also hardware, if that's a significant limiting factor. Okay. One other thing that I wanted to mention is it's not necessarily restricted to stopping the test. If you're in a situation where maybe you have to reserve a test facility, you get the entire week, and let's say this method says, well, after 2 days, the conclusion's obvious, your test is done. Well, you don't want to just throw away those extra days, but you could certainly, right, update your design at that point. Maybe you want to test at different levels, for instance, like a different temperature or something, right? Those are all things that this adaptive nature allows you to try, right? It brings kind of flexibility into your system. Okay. So again, in our situation, this quantity of interest that we wanted to, or our quantity of interest is essentially the reliability of this timing measurement. Again, we want to check what is the probability that the timing of kind of the disconnect is between some value A and B. All right, and so I'm just going to denote that probability here as phi. Okay, and of course there's an actual system requirement that says, well, this probability is going to have to be at least some value that I'll denote as phi naught. All right, and so we want to check, is our quantity of interest phi greater than phi naught? Okay, so, whoops. I'll leave that. All right, so suppose, we design an experiment kind of in the normal way based on this information. We have some maybe information of how to do a power analysis that says, well, we expect to need to run this experiment n times. All right, great. Now, we can use something that's called predictive probability that I'll talk about quite a bit to help maybe make us make earlier decisions during the test. So predictive probability is this probability after seeing just a fraction of your data, so the first n sub o observations, it's the probability that then we would be able to conclude that phi is bigger than our requirement. Okay, so this is the predictive probability in a sense, right? This is from a Bayesian perspective. All right, and so this definition itself is a little bit wordy, and so I'm just going to go through a very simple example, also using coin flips, to try to get this point across of what predictive probability really, what it means. So suppose you're in a situation where you want to determine whether a coin is biased towards, say, heads. All right, and suppose you did some power analysis that said you have to flip the coin 10 times and your experiment is sufficiently powered. Great. And then, say you pick like a significance level or something that says, in order for you to decide that the coin is biased, you will have to see 8 out of 10 flips to be heads. Okay. So let's suppose our first 5 flips end up like this. So your first 5 flips, you see 3 heads. All right, great. You have 5 more flips in your original design. Well, if you think about this, right, the only way at this point that you could reject essentially your null hypothesis, or the only way that you could say the coin is biased based on this criteria is, right, if the last 5 flips are heads. Right, there's no other way that you can get 8 out of 10 heads if out of the first 5, only 3 of them are heads. Okay, so it's certainly possible. And let's, even if you suppose that the coin actually is biased at this case, and say there's actually a 60% chance of flipping heads. At this point, after only seeing 5 coin flips, right, there's only a 7% chance that you would be able to reject your null hypothesis. Okay, so there is a chance, but it's relatively small. All right, and that chance that I'm saying 7%, that is your predictive probability. It is the probability that after seeing some of the data, that you would be able to reject the null hypothesis after seeing all of your data. All right, so consider a different scenario where you observe this in your first 5 flips. Right, so you observe 2 heads during your first 5. Right, well, in this scenario, right, there is no possibility that you can observe 8 out of 10 heads at this point. Even though you've only seen half of your data, you will not be able to reject your null hypothesis. So at this point, you might wonder, is it even worth it to collect the remaining data? Right, if your main objective of your test is to determine that the coin is biased, right, there's probably not a reason to do the remaining 5 flips because it's impossible, right, for your answer to change. Right, and so this is obviously a very toy example, but again, if your main objective can't be, or the answer to your main objective, you might not have a reason to collect future data. All right, and then just one last example just for fun. If all 5 of the first coin flips were heads, there's several combinations that would give you this ability to get 8 out of 10 heads. And again, assuming that the probability of heads is 60%, at this case, there's a 68% chance that you will be able to effectively reject your null hypothesis. So your predictive probability is 68%, which is neither really small nor really big, which is kind of an indication that you, at this point, right, you'd probably want to keep flipping. Okay, so this coin flip illustration obviously is very much a toy problem, but it's meant to represent what predictive probability is actually measuring. Okay, it's not saying that what is true or what is not true, like a posterior distribution would tell you. Right, the posterior or the predictive probability is after you've already assigned resources to your design. And then it's saying, okay, given that these are the resources that I have, what are the possible outcomes? All right, so these are the only equations I have on my slides. So, for those of you who are mathematically inclined, this is the actual formal definition of what predictive probability is. All right, so suppose the data you actually observed, so your first n sub o observations, let those be x, and then the remaining observations that you planned on collecting but have not yet collected, let those be y. All right, so then the predictive probability is defined as the probability under the predictive distribution of y given x, the probability of seeing the remaining y observations such that the probability that your reliability requirement would be met. All right. So, right, that probability of phi being greater than phi naught given x and y, right, that's just a posterior probability at that point, right? Because your quantity of interest is phi, it's just a parameter, right? And so it's just a posterior probability. So it's saying what's the probability of observing data in the future such that I would make, you know, a positive decision about my about my quantity of interest. All right, and so you could run through the math here and look and see, you know, at the bottom line, it shows it's effectively just a function, right, of a posterior distribution and a posterior predictive distribution, all right, which you would normally have. Okay, so once you have a posterior a predictive probability, which we often denote as PP, you can decide to stop testing early and decide and declare that in this example, the reliability is either met or the reliability is not met, which you could loosely translate as, right, rejecting a null hypothesis or failing to reject. All right. So if beforehand you say, I'm only going to stop to say the reliability is met, then you could track that predictive probability. And if it gets to be greater than some threshold, at that point, you could stop your test, save the remaining resources, and say, my reliability requirement is met. Right? You could do the same if, let's say, you only want to stop a test early to say for failure. All right, to say, well, I'm going to collect all my data unless things start to look really bad. All right, and in that case, you'll pick some lower threshold where if your predictive probability drops below some threshold, you'll say, the chance of me observing enough data to reject the null hypothesis is very low. So let's save the remaining resources, make the required fixes, and use those, use that hardware for a future date. All right, and so these thresholds, this theta L and theta U, right, of course, these are going to be user chosen, and they should reflect essentially your relative comfort with making type 1, type 2 errors. Okay, so I'm just going to show you, in this case, a retrospective analysis of that actual experiment here, where again, we're interested in some reliability requirement number. The original design asked us to do 230 polls, which I think took about 2 weeks of labor, again, for maybe 8 or so people. All right. The test engineers up front said, you know, we would definitely need at least 30 polls no matter what. There is no way we'd stop a test earlier than that. Okay. And I said, let's just set the success threshold theta U to be 0.95. So the plot here is showing on the x-axis the number of polls, right, going from 0 up to 230. The black line is actually plotting the predictive probability of that test series. Okay. And you'll notice at about 120 polls, the predictive probability has eclipsed that threshold of 0.95. Right. So in retrospect, what this would have said is at 100, once after that 120th poll was done, and we calculated predictive probability, right? It's eclipsed our threshold. So at that point, if we adhered to this process, where we could have stopped the test early and said, well, the data is suggesting that we will almost surely reject the null hypothesis if we had collected the remainder of the data. So maybe we can just stop now, save all these resources, right? Which in this case would have been essentially half the amount of time. It would have been an entire week of testing for 8 people. Okay. Now, what I haven't addressed yet is, right, this is a very optimistic analysis because predictive probability is also very much dependent upon your model, right? When you calculate it, if you remember the previous equations, it very much depends on your model being correct, right, which becomes a little bit dangerous. So for that reason, we did a kind of a simulation study here to test essentially the robustness of this method, all right? And so for comparison, there's also a frequentist kind of counterpart to predictive probability called conditional power. So we'll compare to that as well. All right. So for the reliability situation, effectively, we just fit a normal model to the data. All right, we assume timing was normally distributed. All right, so we just had essentially a mean and a variance to estimate. All right, so I'm going to calculate type 1 and type 2 error metrics for a couple different sets of analysis. So the first situation is I won't do any interim analyses, so it's just a normal design. Another example, I'll do one interim analysis, which is effectively looking at your data halfway through your experiment. All right, and I'll try to do this for several different iterations of number of interim analyses. So if I do 9 interim analyses, every 10%, I'll essentially look at my data and do a test. All right, and so for the simulation, I use this total sample size of 100 kind of for convenience. All right, so the main metrics that we're going to look at are effectively the type 1 error rate of using predictive probability and conditional power, and then as well the type 2 error rate for both of those. So remember, the model that I'm fitting the data is a normal model. All right, but I'm going to generate data from models that are not necessarily normal. All right, so I can compare what happens when I assume the data is normal, but in fact the data is not normal. All right, so here first is when I only consider stopping early to declare a failure. All right, so to declare that I will not reject the null hypothesis. All right, so each row is corresponding to a different true data generating distribution. Right, so the first one is normal, which I'm assuming the data is normal, and then I actually simulate from a normal. Right, and then a couple other distributions, a Laplace, 2 different gammas, so I have some skewed and a uniform. Okay, in blue is the predictive probability, in red is conditional power, and then on the left side are the type 1 error rates. So if you look at that, you can kind of see for the most part, all the type 1 error rates are below kind of the nominal threshold of 0.05. It does appear that conditional power has a little bit higher type 1 error rate than predictive probability, but nonetheless, they all look pretty good, even as I continue doing additional interim analyses. Okay. When you look at power, though, you notice the power tends to decrease as I do more and more interim analyses. And this should make sense because I'm only stopping to declare failure. So essentially, I'm giving myself multiple chances in this situation to make a type 2 error. All right. But what you might notice is predictive probability, as you do more interim analyses, predictive probability tends to kind of give better power than conditional power. All right, and of course you see some degradation as our model does not match the true data generating mechanism. You know, going from if the data generating mechanism is actually gamma, right? Our power is almost half of if the data was actually normal. All right. On the other side, we could also stop for success only. All right, and so there, when we look at type 1 errors, especially for conditional power, you see a concerning issue there. All right, as the number of interim analyses increases, the conditional power actually starts to blow up. And this, I will mention, is after correction. So I have already applied an alpha spending curve to conditional power. So I've already added a correction, and it still kind of overcomes that. Predictive probability actually does quite well and kind of controls that type 1 error. All right. On power, we almost see the flip again, where conditional power tends to actually have higher power than predictive probability, really for all these scenarios. Okay, and overall, what that's kind of saying is it seems like conditional power is being a little bit less conservative than predictive probability, which isn't necessarily surprising since the Bayesian method is integrating over its uncertainty. We did another analysis quick for, you could think of it as a reliability scenario if your data was pass-fail, all right, instead of a normal model, just binary data. And so here's some results, again, using predictive probability versus conditional power for type 1 error rate, type 1 error rate powers. And these results are actually kind of hot off the press and are a little bit surprising. They actually show kind of the opposite of what was going on with the normal data. And in this case, you're seeing predictive probability actually being less conservative than conditional power. All right, so this is actually quite surprising. I don't necessarily have an answer for why this is the case yet, but I just thought it'd be interesting to show some of these new results. Okay. Another thing you might wonder is, well, how do we decide when to first look at the data? And I don't think we have a good answer for that yet. We did an analysis with the simulated data to come up with an idea of, well, after about observing the first 30%, we tend to make pretty good decisions. If we started looking at the data before observing the first 30% of the data, we had issues, and results were, I would say, quite a bit worse than, if we waited till at least to the 30% of the experiment was collected. All right, so the point of this was predictive probability is a tool you can use as a part of an adaptive design of experiments regime, all right, to essentially save resources, money, time, labor. Predictive probability is actually different than posterior probability, right? Because predictive probability is after you've assumed you have a set amount of resources for a design. Okay. Overall, with the normal model, the predictive probability appeared to be more conservative than the frequentist alternative. I didn't talk about priors at all, and if you have questions, we can talk about that. Another thing that I wanted to note was there might be a concern about stopping tests early, right? Given the nature of the type of testing we do, it tends to be high consequence scenarios. And I just want to mention that predictive probability, a lot of this work originated in the clinical trials arena, right? So they have been the ones who have essentially been at the forefront of adaptive methods. And so I think they certainly also understand kind of the nature of high consequence decision making. So we shouldn't be afraid for that sole reason to use approaches like this. All right, so that is all I have. Thanks for listening.
All right, we have time for one question. I don't see any online yet, but does the room have one? All right.
Thank you. So this is just related, I think, I think on slide 6, that was kind of from the DOE designing it in the regular way, so to speak. So that seemed like that was for multi-factor experiments, perhaps. So have you thought about, if you know that you perhaps might stop at N naught, so instead of randomizing the rows, kind of optimizing to say, I'm going to try to get the best bang for my buck at that first stopping point?
Yeah, exactly. I think the way you would design an experiment, if you think you're going to be potentially stop it early, would definitely be different than if you assume you're going to gather everything.
Yeah, great. Thanks.
All right. Thank you very much.